In this video, we're going to look at a quick summary of the electrophilic aromatic substitution reactions of benzene, as well as the general mechanism and the sigma complex that is formed. So here's a quick rundown of the different reactions that we will look at. We see this first one here on the left. We are exchanging the hydrogen on the benzene ring with X, which is the common abbreviation for a halogen. So this is called halogenation. The second example, we're replacing that hydrogen on the benzene ring with a nitro group, an NO2 group. So this is nitration. Next example, we're replacing the hydrogen with an SO3 group. This is sulfonation. Next, we're replacing it with an R group. This is alkylation. That R group is just an alkyl group. Last example, we're replacing it with a carbonyl group. This is acylation. And we will go into each of these in more detail in later videos, but for now, recognize kind of the name with the transition that's happening, and then next we're going to look at just a general mechanism. So the specific mechanisms for each of these reactions will vary slightly, though most of them will all have a different first step to prepare your reagents. The sigma complex that forms, which we'll talk in more detail about, is pretty consistent from one reaction to another, so it's worth looking at a general mechanism. So the first thing that's always going to happen, you'll have your benzene. And if you're just working with plain benzene, no substitutions on it, it doesn't matter which double bond you're focusing on, because remember, you don't really have double and single bonds anyway. So I always like to think about the two hydrogens that are attached to one of the double bonds. I draw them out, it helps me see what's going on. So the first step is your benzene, which is going to be the nucleophile, 2 electrons in your pi orbital, are going to attack whatever the electrophile happens to be. And the electrophile is going to vary from one reaction to another. That electrophile is usually attached to something with a negative charge, so we're going to be breaking whatever that bond might be. And then we will have what was our benzene ring. We do lose aromaticity here. We're no longer conjugated. Our hydrogens that were there are still there. E is now bonded to that ring. And then this lower carbon, the other carbon that used to be part of the double bond, only has 3 bonds. So now it has a positive charge. And we also formed whatever Y- happens to be. This here is the sigma complex, and on the next slide we'll talk about the stability of that sigma complex. Because remember, we're breaking aromaticity here. That's not an easy thing to do. The fact that that sigma complex is stabilized by resonance helps us actually go through that step. So now what's going to happen so that we can reform our aromatic ring, some base, likely whatever Y happened to be, is going to come remove the hydrogen from the carbon that now has E attached. Those electrons are going to shift down to reform our pi system. So now we're back to benzene. That lower hydrogen is still there. The upper hydrogen has now been replaced with whatever our electrophile happens to be. So in most double bond reactions, this would look similar to an addition reaction up until this second step. You would kind of think, well, that negative charge should attack the positive charge. It's very tempting to do, right? But that doesn't happen. It's not an addition reaction because it's more stabilizing to reform that double bond and reform the aromaticity. So let's look a little bit more at this sigma complex that we saw on the previous slide. So the sigma complex is the positively charged intermediate that forms. So the generic one we had our electrophile add, and there's our positive charge. Like I said, to make this we had to break aromaticity, so the driving force of this is that we do have resonance. So we can kick these electrons around, which is going to shift that positive charge around the ring and delocalize it. So now the double bond is here. This other double bond hasn't moved. So now this carbon is lacking the third bond. Shift another set of electrons around. So now the lower bond, double bond hasn't moved. That upper one shifted to the side. Positive charge is now up top. And those are our three resonance structures for the sigma complex. Now, depending on what E is as your electrophile, you could have some resonance that actually moves out into that group as well. But for the generic version here, these are the three resonance structures that we have for the sigma complex.